Hi everyone, this is Mike with a video about finding zeros of polynomial functions. I want to do several examples because I've been getting some questions about how to tackle these problems, I think essentially from start to finish, to get an idea of what it really looks like to find zeros of these functions. So I've got three different examples here, and I'm going to show you the process by which I think you should be finding these zeros. Keep in mind that this is not the process as it has always been. Of course, we've not always had computers and tools like Desmos to help us. And to the extent that we did not have tools like Desmos and graphing calculators to assist that work, we have things like Descartes' rule of signs and the rational zeros theorem. Those, along with some of the other theorems you've been watching videos about and reading the textbook about, were tools that have been used in the past when we didn't have graphing tools like this in order to find zeros and x-intercepts. But because we have those tools at our disposal, then I want to show you how they become part of the process. And I'll just mention here that for the exam, to the extent that I want you to use a graph to help you in this process, I will provide the graph. You don't necessarily have to have a graphing calculator or Desmos with you during the exam. So let's tackle these one by one, and hopefully we'll be able to help you understand this a little bit better for those of you that are having some trouble. So let's start with this graph. This is a really ugly looking polynomial, but it turns out to be a really easy example. It looks like this. I can zoom out a little bit on the graph, and you can see, well, that minimum is quite low there. So it goes all the way down, looks like to about -80. But what I care about in this polynomial is where the graph crosses the x-axis. A key idea in this entire thing is about where the graph crosses the x-axis. That is also the same thing as a zero. The reason for that is because the term zero comes from the x values that make the y value equal to zero. And if the y value is equal to 0, then that means that I'm on the x-axis. So when I look at the graph of these functions, the place that I care about when I'm looking for zeros, the place that I care about is the x-intercept. And a graph like this one and a tool like Desmos enables me to just click on the graph, and I will locate 3 zeros. So you can see one of the zeros is at x equals -3, another is at 1/2, and the third one is at 2. So I can verify that. Of course, the graph is telling me that those are zeros because you can see the y values are all 0. But I can verify that using this process. So I can use synthetic division. So I'm going to try that here. It's going to take me a minute just to translate everything over. So actually, no, I do not need to do the x's if I'm using synthetic division. So let's cancel that. So remember, synthetic division, I'm going to choose one of these values. So I'm going to choose -3 as my 0. So that's going to go here. -3 will go in a little box like this. And then I'll have my leading coefficient there. Let's get the other coefficients, -3, -15, and +32. And then -12. So synthetic division, I'm going to bring this leading coefficient down, and then I'm going to multiply, and then I add these two values together to give me -9. Multiply again. -3 times -9 gives me 27. When I add, I get this. Multiply again and add to get this. Multiply again and add to get 0. So that is a verification that my 0 of -3 actually is a 0. So that's a good thing. We're going to call that -3. That's going to work. Okay. And then that leaves me with this polynomial as a remainder. So these are all x values here. This is an x to the 0 power, so that's actually a constant. That's to the first, to the second, and to the third. So my next synthetic division is going to have these coefficients, the same coefficients that I just finished with. That's a positive 12 and a negative 4 here. I don't need to include the remainder. And I'm going to use my other 0 here, 1/2. That was the other 0 that I found, or one of the 3. And so then I bring down the 2 here, multiply and add, and then multiply again and add, and then multiply again and add. And again, that remainder of 0 tells me that 1/2, it confirms that 1/2 is actually a 0 like I thought. And that leaves me with x's here and here. Again, this last 8 here is a constant, so it's x to the 0. This is x to the first, and this is x squared. Now from here, I can actually just factor this polynomial, this quadratic polynomial that remains. But just to show you how this process continues, I'm going to take the other 0, which was a positive 2. I'm going to take the other 0, and I'm going to do synthetic division on that with these coefficients right here. So 2, negative 8, and positive 8. Again, that quadratic is factorable, and I would encourage you to go ahead and factor it. But if this had been a larger polynomial, you just keep this process going. So I'm going to bring the 2 down and multiply, and then I add and multiply. Oops, sorry, not negative 8, but negative 4. And then multiply again and add. There's my remainder of 0. That's a constant. That negative 4 is a constant. And then that gives this as my remaining equation, which I can easily solve to get another value of 2. So notice I have 2 values of 2 that are zeros, and the graph actually says that as well. Notice this value of 2 is a 0 that bounces off the x-axis, which tells me that it has an even multiplicity, and that confirms the fact that I had 2 versions of that 0 in my polynomial. So again, this is a really easy one because the graph shows all of these zeros pretty directly. So what happens if it doesn't necessarily show all of the zeros quite so nicely? So here's another example where I've got 2 zeros that are kind of ugly decimals and a third 0 that is a pleasant integer. And so again, this is all the fundamental theorem of algebra tells me that I have 3 zeros total, and that's what I should have because this is a degree 3 polynomial. So these are all of the zeros, but these are just decimal approximations. The question is, are these fractions or are they ugly square roots, or what might they be? So in order to find that out, again, I'm going to use synthetic division on the 0 that I do know, which is 4. So let's take a different polynomial here and a different 0. There's my 0, and I'm going to put in 1, negative 6, 7, and 4. Those are the coefficients of the polynomial. Do the synthetic division. There's my remainder of 0 telling me that my 0 actually was a 0, so that confirms, again, that 4 was actually a 0. And now I know my polynomial that remains looks like this. And that's, again, something I can solve instead of using synthetic division on this one. Again, not knowing what those decimal values actually refer to, I'm going to go ahead and solve this like I would any other quadratic equation. I'm going to use the quadratic formula. So the opposite of b, plus or minus the square root of b squared, minus 4 times A times C all over 2 times A. And when you do that, you get x equals 2 plus or minus the square root of 8 over 2, which you can simplify down to 1 plus or minus the square root of 2. And those two values actually are going to match. If we go here and say 1 plus the square root of 2, you'll notice that that's one of the zeros that I had, and 1 minus the square root of 2 is going to give me the other 0. So you can see this 0 here, this negative 0.414 matches that 0, and this 2.414 matches this 0. So these two zeros as shown are just decimal approximations. The exact values are given here, and the way we found those exact values was to use synthetic division on the 0 that was an integer, x equals 4, and then we used the quadratic formula to find the other 2. So that gave us a total of 3. And I guess if we were going to write the final answer for all the zeros, it would look like this. And there are our 3 zeros for that polynomial. Okay, last but not least, we're going to move on to this polynomial. And like the previous one, this is a quartic polynomial, and so it has 4 zeros, but all I can see are 2 of them. And again, luckily both of these happen to be integers. So in order to verify what those zeros are and to help me find the other 2, I'm going to use synthetic division as I did before. So one of my zeros is going to be negative 3. And I'll go back to my coefficients. 1, 2, negative 2. 1, 2, negative 2. I think then it was a 2. And then a negative 3 at the end there. So synthetic division here, I'll bring down the 1 and multiply. And then add and multiply again. And add, multiply again, and add. And finally multiply there and add to get a remainder of 0. And then as before, this leaves me with a polynomial that I can then do synthetic division on one more time. And my other 0, recall from the graph, was x equals 1. So performing the synthetic division, there's my 0 that tells me that my remainder of 0, which tells me this actually was a 0. And now my remaining polynomial looks like this. And that I can solve pretty quickly just by subtracting 1 and then taking the square root. And you can see that those two zeros are imaginary, which is why they do not appear on the graph. And so my zeros in that case are going to be x equals, what were the two from the graph? Negative 3 and positive 1. And then I and negative I. So there you have 3 examples from start to finish of finding the zeros of a polynomial. And in every case, your main job is to start with the graph itself, pick out the easy zeros, and you can use the fundamental theorem of algebra to find out if you've found them all. So in the first example in the purple, we could have really just stopped with the graph and said, oh, look, those zeros are negative 3, positive 1/2, and positive 2, noting that positive 2 is a 0 of multiplicity 2 because of the bouncing. And then in this second example, we can look at the graph and notice that, well, 2 of those zeros are ugly decimals, so we're going to have to do a little bit of work to find that. But we can find those using the information we get from the nice integer 0 of x equals 4. And then in some cases, we're not going to see all of the zeros. We're only going to see some of them. And we'll use the same technique on the zeros that we have in order to find the other zeros that we cannot see. So that is the process of finding zeros. I hope you've been able to get something out of this video. But of course, as always, if you have questions or concerns as you work, please let me know. Keep working hard.